The situation in this question is the following. This car is moving to the right until it meets a hill which is inclined 18 degrees with respect to the horizontal. This car is moving at 95 kilometers per hour. We then have to discover what is the minimum radius of this transition section such that the car do not leave the road. So this is the radius. It's the radius of this circle, and we have to discover what is the minimum value of r such that the car do not fly away when passing through this transition. For that, let us analyze closer what is this transition region. So this is a zoomed in transition region. Notice that the transition is nothing else than a section of a circle. So during the transition, the car is undergoing a circular motion. Then we can treat it as usual. The condition that the car never leaves the road translates to the condition that the normal is bigger than or at most equals to 0. So the condition is the following. The normal force must be bigger than or at most equals to 0. But now, what does the normal force has to do with the radius of the circle? For that, you have to remember a few bit about the centripetal force. So whenever an object is undergoing a circular motion, there is a centripetal force acting on that object. And that centripetal force is given by the mass of the object times the velocity of that object squared divided by the radius of that trajectory. But then what does the centripetal force has to do with the normal force? It happens that the centripetal force is the net force that is acting on the radial direction, which is the direction that passes through the center of the trajectory. Then you can see that in any situation, the normal force is part of the centripetal force. But obviously, the normal force isn't the whole thing. There is also a component of the weight force that is composing the centripetal force. And let me call this component the radial component of the weight force, and it is like this. So this is WR. The other component of the weight force would be this one, the tangential component, which I'm calling WT. Notice that this angle is the same angle as this one, because we have two parallel lines that are crossed by a straight line. Then we can also say that this angle is equal to theta, and then we are able to relate the weight with the radial component of the weight. Using that triangle, we have the following. This is the triangle, and then this is the 90-degree angle, this is the hypotenuse, this is WR, and this is WT, and this is theta. You can see that the cosine of theta in that context is given by the adjacent side, so the radial component, divided by the hypotenuse, which is the full weight. Then the radial component is equal to the weight times the cosine of theta. Therefore, we can write the centripetal force as follows. At any point of the circumference, the centripetal force is given by the radial component of the weight force, which is pointing to the center, so it's positive, minus the normal force that is pointing outwards. This is equal to the mass times the velocity squared divided by the radius. Then, in the limiting situation, where the normal is very, very close to 0, so that we can say that it is effectively 0, we can say the following. The radial component of the weight force must be equal to mv squared divided by r. So the radius must be equal to mv squared divided by the radial component of the weight force. Using the equation for the radial component of the weight force that we had just derived, we get the following. mv squared divided by w times the cosine of theta. Now remember that the weight force is given by the mass of the object times the acceleration of gravity. So this can be written as mv squared divided by mg times the cosine of theta. We can simplify the masses, and then we get an equation for the radius. The critical radius is v squared divided by g times the cosine of theta. We already know what is v, we know what is g. Actually, we remember that g is approximately 9.8 meters per second squared. So the only thing that we are left to discover is the value of this angle theta. For that, we have to use the geometry of the situation. Notice the following. This angle between this line and this line is 18 degrees. But the angle between the black line and this red line is 90 degrees. I can extend this line so that it's easier to see. So as you can see, there is a 90-degree angle here. Then, with that in mind, we can determine what is this angle, because we know that this whole angle is 90 degrees. Then, this angle must be 90 minus 18 degrees, which results in 72 degrees. This is this angle. But notice that the angle between the radial direction and this blue line is also 90 degrees. So this angle is an angle of 90 degrees. Therefore, we conclude that theta plus 72 degrees must be equals to 90 degrees. And the only possibility for that result is that theta is also equals to 18 degrees. Now that we know theta, we can finish the question. So the radius is given by 95 kilometers per hour. We should convert this 95 kilometers per hour to meters per second. For that, we divide it by 3.6. So the velocity is 95 divided by 3.6 meters per second, and this is squared. And then we divide by 9.8 times the cosine of 18 degrees. And this results in a radius of approximately 75 meters, which is the minimum radius of the transition region.